The electromagnetic force between charged particles is one of the fundamental forces of nature. We begin this chapter by describing some of the basic properties of electric forces. We then discuss Coulomb's law, which is the fundamental law governing the force between any two charged particles. Next, we introduce the concept of an electric field associated with a charge distribution and describe its effects on other charged particles. We then show how to use Coulomb's law to calculate the electric field for a given charge distribution. We conclude the chapter with the discussion of the motion of a charged particle in a uniform electric field. Let's begin. Properties of electric charges. A number of simple experiments demonstrate the existence of electric forces and charges. For example, after running a comb through your hair on a dry day, you will find that the comb attracts bits of paper. The attractive force is often strong enough to suspend the paper. The same effect occurs when materials such as glass or rubber are rubbed with silk or fur. Another simple experiment is to rub an inflated balloon with wool. The balloon then adheres to a wall, often for hours. When materials behave in this way, they are said to be electrified or to have become electrically charged. You can easily electrify your body by vigorously rubbing your shoes on a wool rug. The electric charge on your body can be felt and removed by lightly touching a friend. Under the right conditions, you will see a spark when you touch, and both of you will feel a single slight tingle. Experiments such as these work best on a dry day because an excessive amount of moisture in the air can cause any charge you build up to leak from your body to the earth. In a series of simple experiments, it is found that there are two kinds of electric charges, which were given the names positive and negative by Benjamin Franklin. To verify that this is true, consider a hard rubber rod that has been rubbed with fur and then suspended by a non-metallic thread as shown in the figure. When a glass rod that has been rubbed with silk is brought near the rubber rod, the two attract each other. On the other hand, if two charged rubber rods are brought near each other as shown in second figure, the two repel each other. This observation shows that the rubber and glass are in two different states of electrification. On the basis of these observations, we conclude that like charges repel one another and unlike charges attract one another. Using the convention suggested by Franklin, the electric charge on the glass rod is called positive and that on the rubber is called negative. Therefore, any charged object attracted to a charged rubber rod or repelled by a charged glass rod must have a positive charge, and any charged object repelled by a charged rubber rod or attracted to a charged glass rod must have a negative charge. Attractive electric forces are responsible for the behavior of a wide variety of commercial products. For example, the plastic in many contact lenses, a film cone, is made up of molecules that electrically attract the protein molecules in human tears. These protein molecules are absorbed and held by the plastic so that the lens ends up being primarily composed of the wearer's tears. Because of this, the wearer's eye does not treat the lens as a foreign object and it can be worn comfortably. Many cosmetics also take advantage of electric forces by incorporating materials that are electrically attracted to skin or hair, causing the pigments or other chemicals to stay put once they are applied. Another important aspect of Franklin's model of electricity is the implication that electric charge is always conserved. That is, when one object is rubbed against another charge is not created in the process. The electrified state is due to a transfer of charge from one object to the other. One object gains some amount of negative charge while the other gains an equal amount of positive charge. For example, when a glass rod is rubbed with silk, the silk obtains a negative charge that is equal in magnitude to the positive charge on the glass rod. We now know from our understanding of atomic structure that negatively charged electrons are transferred from the glass to the silk in the rubbing process. Similarly, when rubber is rubbed with fur, electrons are transferred from the fur to the rubber, giving the rubber a net negative charge and the fur a net positive charge. This process is consistent with the fact that neutral uncharged matter contains as many positive charges, protons with atomic nuclei, as negative charges, electrons. Robert Millikan discovered that electric charge always occurs as some integral multiple of a fundamental amount of charge, E. In modern terms, the electric charge Q is said to be quantized, where Q is the standard symbol used for charge. That is, electric charge exists as discrete packets, and we can write Q equals NE, where N is some integer. Other experiments in the same period showed that the electron has a charge minus E and the proton has a charge of equal magnitude but opposite sign, plus E. Some particles, such as the neutron, have no charge. A neutral atom must contain as many protons as electrons. Because charge is conserved quantity, the net charge in a closed region remains the same. If charged particles are created in some process, they are always created in pairs whose members have equal magnitude charges of opposite sign. From our discussion thus far, we conclude that electric charges has the following important properties. Number one, two kinds of charges occur in nature with the property that unlike charges attract one another and like charges repel one another. Second, charge is conserved, and third, charge is quantized. Now here a quick lab. Rub an inflated balloon against your hair and then hold the balloon near a thin stream of water running from a faucet. What happens? A rubbed plastic pen or comb will also work. Now second thing, quick quiz. If you rub an inflated balloon against your hair, the two materials attract each other as shown in figure. Is the amount of charge present in the balloon and your hair after rubbing A less than, B the same as, or C more than the amount of charge present before rubbing? Answer these questions and we meet in the next section. Thank you.